Hi students, here's your second video lesson for radioactivity. We're just going to do a little bit of a radiation review here based on what we did last time. There are three kinds of decay that we talked about last class in the challenge. The first kind was alpha decay. And alpha decay is when we have a positive alpha particle, or helium nucleus, emitted from a radioactive substance. And here's the symbol. You'll notice that there's a mass change of 4 because of the helium nucleus having 2 protons and 2 neutrons, and a difference in atomic number of 2 because it's helium with the 2 protons. Alpha particles are the least penetrating of the decay particles, mainly because they're really big compared to the other ones, so they have a greater mass and therefore travel at a lower energy. So if we want to show alpha decay in an equation, well, right here I've set up an equation, protactinium 231. Protactinium has an atomic number of 91, and so we know that since we're losing 2 from our atomic number, we're going to be going down to 89. And if we look on our periodic table, that turns out to be actinium, which is AC. And we need to lose 4 from the mass, and so this will now become actinium 227. Now, of course, you'll notice that this isn't done because it's not balanced. We also have to show the particle that's emitted, which happens to be helium. And so helium would have a mass of 4, atomic number of 2, and we can either show the alpha symbol or the He. I'm going to show the alpha symbol just for the case of this. The second kind of radiation that we talked about last class was beta decay. This is where we have a negative beta particle, or simply just an electron, emitted from a radioactive substance. And here you can see our symbol is beta symbol with a -1 for the atomic number, which will be really important, or using our electron here. And the way that this occurs is a neutron decays in the nucleus into a proton and an electron. And the electron is then emitted from the nucleus. And so here we have sodium 24, and its decay process, according for beta decay, is going to keep the same mass, but our atomic number is going to increase by 1. And so this then turns into magnesium. And of course we have to show the particle that's emitted, so no change in mass, and a change in number right here. Okay? The third kind of radiation that we talked about was gamma decay. And this is where rays of high energy and low wavelength, or really short wavelength radiation, are emitted from a radioactive substance. This occurs from the redistribution of energy in a nucleus. It's really important to remember that there is no mass change whatsoever and no element change whatsoever. Furthermore, gamma decay has the greatest penetrating power of the three types, in that it can penetrate, all sorts of metals, basically only stopped by a big powerful lead block. Gamma decay, we show this through another equation where we're going to end up with the same mass and the exact same atomic number, as you know, but this time we have no star on the product side. We still have to show our zero change, and that's our gamma particle right there. This little star just shows that we're going from a higher energy state to a lower energy state. Something that's really important is for all three types, the sum of the mass numbers must be equal on both sides of the equation. So you'll notice here 234, 234, 90, 90, and of course the zeros had nothing. And I'll go back here, 231 is equal to 227 plus 4, and 91 is equal to 89 plus 2. So everything is equal here in terms of the mass numbers. 24 is 24 plus 0, and of course 11 equals 12 plus -1. So I got a bit ahead of myself. I also explained that the sum of the charges can't change either, and so the atomic numbers will also stay the same. If you do want some extra practice, with this radiation stuff, on page 229 in your textbook, there's an activity, 7-1C. You can do that at home if you'd like. So now on to our next concept, being half-life. And this is where things, I think, get pretty awesome. Here's a picture of a Tyrannosaurus Rex that I took at the American Museum of Natural History in New York last year. And it's estimated to be between 65 and 67 million years old, which is just phenomenal. But of course it begs the question, how on earth do we know? Were there any humans back then observing T-Rexes, recording things down in a journal that we could then pass down through the ages? Of course not. So there has to be some way that as scientists we can figure out how things are this old without direct observation. So if we want to know the age of some sort of substance, well, based on these 3 points here, we can figure it out. The first point is that all organic and inorganic matter contains isotopes, such as carbon and potassium, in constant ratios. So we might have carbon 12, carbon 13, carbon 14, all in constant ratios in one kind of living organism. Potassium, 39, 40, and 41, again in constant ratios in that same organism. Once this living organic matter has died, this unstable isotopes, such as carbon-14, will decay at a constant rate into stable isotopes such as carbon-12. Different isotopes have different rates of decay, but if it's, say, carbon-14, carbon-14 will always decay at the same rate, no matter what the environment is, no matter what the temperature is, anything, always the same rate. So based on that, we can measure different amounts of unstable isotopes remaining in that decaying matter. And this is usually measured via half-life. So if we want to learn more about half-life, well, we should learn how to represent it. All radioactive decay follows a pattern called the decay curve, where all isotopes decay by 50%, or half of their original amount, in a substance in a constant period of time. So for example, strontium-90 decays by 50% every 29 years. And so in this chart you can see 0 half-lives will be 0 years, there will be 100% strontium-90 present. After 1 half-life, there will be, which is 29 years, there will be 50% of strontium-90 remaining. After 2 half-lives, which is 58 years, there will be 25% remaining. 3 half-lives, 87 years, 12.5% remaining, and after 4 half-lives, which is 116 years, only 6.25% of that original strontium-90 is remaining. This is really simple to draw in these decay curves. So here's a graph right here where we can draw our decay curve. And our y-axis is going to be the amount of strontium-90 in terms of a percent. And down here, this is the number of half-lives, which we know for strontium-90 is 29 years. And so when we have strontium-90 at 100%, there have been 0 half-lives. It's basically just been formed. But 1 half-life, 50% of strontium-90 remaining, will be right here. After 2 half-lives, we'll expect 25% remaining. After 3 half-lives, we will expect 12.5% remaining. And after 4 half-lives, we'll be at that 6.25% remaining. And so now what you'll notice is that this occurs via a nice curve which gets closer and closer to the asymptote as it goes down. This decay curve you'll see no matter which type of radioactive substance we'll be using. So whether it's strontium, whether it's carbon, or radium, this decay curve will always be the same. The only thing that changes is the length of half-life. So half-life is how scientists can figure out how old things are without direct observation, such as counting the rings of a tree. For example, here's Lucy. Lucy is the earliest known hominid, which means that she is the earliest linkage of humans. Lucy is 3.2 million years old and belongs to Australopithecus afarensis species. Of course, this is pretty impressive because we can still see the jawbone, the humerus arm bone, ribs, part of the spinal cord, the pelvis structure, and a femur. So that wraps up our lesson on half-life, which sets us up for today's challenge. We're going to be looking at the decay of carbon-14 and a few other different isotopes, as well as common isotope pairs and the potassium-40 clock. Good luck!